So in this video, I'm going to show you how to assign oxidation states. You want to go back and read your notes on redox reactions or oxidation reduction reactions, because you'll need to know that in oxidation reduction reactions, what we're doing is we're keeping track of the electron flow. So electrons get transferred in these reactions. How do we keep track of how many electrons get transferred? Well, we assign oxidation states to each species in the reaction, or each element in the reaction, and then we track those changes as the reaction moves forward. So we need to assign oxidation states. There are rules for assigning oxidation states, so you want to have those in front of you as you're practicing these problems. So let's start with something simple like methane. CH4, 1 carbon atom and 4 hydrogen atoms. Now, there's no ions present, so we're not assigning charge, we're assigning oxidation states. There's a rule that says the sum of the oxidation states must equal the net charge on the species. So methane, CH4, is neutral. There is no charge up here. So that means when we add up the oxidation states for all of these elements, it should equal 0. Another rule, hydrogen, we always assign +1. So carbon, we need to go find the oxidation state for carbon. So let's use this rule, right? The sum of the oxidation states should equal 0. So there's 1 carbon atom, so I'm going to write 1 times carbon. We're going to add 4 hydrogen atoms. There are 4 hydrogen atoms, and each hydrogen atom has a +1 charge. When we add all that up, the oxidation state should be the same as the charge. Well, here, methane has no charge, should be 0. So that's why it's useful to know the oxidation state on hydrogen. So by rule, it's a +1. So 1 carbon, 4 times 1 is 4. That's going to equal 0. So clearly, carbon has an oxidation state of -4. Now, I'll stress, -4 +1, these are not charges. We're assigning oxidation states. Let's do another one. CO2, carbon dioxide. There's a carbon atom, and there's an oxygen species or oxygen element. There's 2 oxygen atoms. Again, the sum of the oxidation states should equal the net charge. For carbon dioxide, the net charge is 0. By rule, oxygen is going to be assigned a -2 charge. Carbon, we don't know, we need to go find it. So 1 times carbon plus 2 times, because there's 2 oxygens, 2 times -2 is equal to 0. 0 because that's the net charge on the molecule. Carbon dioxide is neutral, so that's why there's a 0 there. So 1 times carbon is just carbon, plus 2 times a -2 is a -4. So plus a -4, that turns to -4. So the oxidation state for carbon, in this case, plus 4. And so you'll notice in the first two examples, we use rules to give us oxidation states for some of these elements. But for carbon, elements like carbon, they can have different oxidation states. Let's do another one. Ammonium, NH4 plus. We need to assign oxidation states for nitrogen and hydrogen. One of the things that stands out, of course, is now we do have a net charge on this species. NH4, this whole molecule does have a net charge, which is a positive 1. Now, that doesn't change the rule for hydrogen. Hydrogen is still a plus 1 for sure. But it does change how we approach this just a little bit. Remember, the sum of the oxidation states should equal the net charge. Up here, the net charges were 0 and 0. Here, the net charge is plus 1. So 1 times nitrogen plus 4 times the hydrogen, which is plus 1, is equal to plus 1 because that's the net charge. 4 times 1 is 4, is equal to plus 1. So here we do a little bit of algebra, right? Minus 4 on both sides. So the oxidation state for nitrogen is a minus 3. Let's do another one. Nitrate. Nitrogen atom and an oxygen atom. Again, you'll notice something that stands out. Nitrate is a polyatomic anion. The net charge is -1. By rule, oxygen is always a -2. So now we need to do some work to go get the oxidation state for nitrogen. So 1 times nitrogen plus 3 oxygen, so 3 times a -2. And all of this should equal the net charge, which is -1. 1 times nitrogen is just nitrogen. 3 times -2 is -6, so this becomes -6. This is equal to -1. Add 6 to both sides. So just like carbon, you notice with nitrogen, it can exist with different oxidation states. Finally, I'll give you one more. Potassium dichromate. There's a potassium ion. There's a chromate. The chromate is CR2O7, and here's oxygen. Now, when you see something like this, remember to be very careful to check what you're looking at. Potassium dichromate. Dichromate is a polyatomic anion. That means that potassium has to be a cation. So this isn't just neutral potassium. This potassium has a charge on it. So there are 3 species here, or 3 species we need to assign oxidation states. There's a rule that says oxygen is a -2. And there's another rule that says monatomic ions. So we haven't seen monatomic ions in our previous examples. Here we have a monatomic ion, which is that one element or that one atom that gains or loses electrons. In this case, potassium is an atom that loses one electron, so it becomes K+. The monatomic ion, the oxidation state is the same as the charge, +1. So make sure you check for those ions. Now again, the potassium is a +1, but what we're looking at here is the oxidation state. So now we can find the chromium. 2 times the potassium, 2 times 1, 2 times the chromium, which that's what we're looking for, and 7 times the -2 for the oxygen. The potassium dichromate, this is a ionic compound. Remember, for ionic compounds, those positive and negative charges have been balanced, so that should equal 0. 2 plus 2Cr, 2 times a negative, 7 times -2 is -14. 2 and -14, that's a -12, is equal to 0. We want to get the unknown by itself. Now here's a little bit different thing that we haven't seen yet. 2 times chromium. So we got to get chromium by itself by dividing both sides by 2. So in this example, chromium has an oxidation state of +6.